Hi, and welcome. Today we're gonna talk about how we generate pulse width modulation signals. So, by saying pulse width modulation (PMW), it's a technique where the duty cycle of a signal can be varied to control the average voltage. For example, let's take like 1 kilohertz pulse width modulation signal. And if we're going to do this on DE10 lights clock frequency of 50 megahertz, and in order to achieve a 1 kilohertz PWM, the counter must count to counter max. That is like the clock frequency divided by PWM frequency minus 1, and this should be 49999. So that's how we're gonna put it this way, because the clock frequency is 50 megahertz and our divided by 1 kilohertz PWM. So this you will come up with 49999. So the duty cycle is determined by comparing the counter value with the threshold. If the counter is less than the duty cycle value, the output is high. So as it says, like right here, we can see, let me sure, yeah, like we can generate about 50% duty cycle on do verifying it via oscilloscope. So now in the lab, what we're gonna do is like to modulate the PWM signals to simulate a sine wave. That's the purpose. So the sine wave is simulated by varying the PWM duty cycle over time. So how it's done? This is done by using two steps, and then the third step. The first is assign lookup table LUT, storing pre-computed sine values. So first of all, you have a sine lookup table. So store pre-computed sine values. Then a phase counter that steps through the LUT at the desired sine wave frequency. So the PWM signal is updated every PWM period to modulate its duty cycle. So let's say if you have one signal PWM, so you have to update PWM period to modulate it after a certain period of time. So after every, we will see after how many milliseconds we have to do this. So ensure you can generate a PWM modulated signal that accurately mimics a sine wave. What we actually have to do, we have like a DC thing, the square waveform. So we have to make it sinusoidal. So we have to mimic in such a way that we can demonstrate as we can see it here. So how to do this? We will implement the frequency control for the sine wave generator using the push button on D10 light FPGA board that you already have with you. So on that you will see a push button. So the push button will allow you to dynamically adjust the frequency of the sine wave with a predefined range. So what's our range? So let's say the range is 1 kilohertz to 5 kilohertz. So you can push the button accordingly to do it within the predefined range. So this is achieved by modifying the counter limit in PWM generator. So if you modify the counter limit in PWM generator, you can do it, which directly affects the period of the output waveform. So this is what we are actually doing. We are just playing with. We are trying to mimic that DC kind of a signal into AC. So which directly affects the period of the output waveform. So we will use debouncing logic to ensure reliable button inputs. So that's we're gonna do in this lab. The frequency adjustment logic will be integrated into the Melee FSM, ensuring smooth transition between frequencies without disrupting the PWM modulation. So we have to verify the frequency adjustment functionality by observing the output waveform on an oscilloscope or logic analyzer. So LED indicators on the D10 light board can also be used as a naive way to provide visual feedback. So um, as defined before, this would be the marking criteria. So we have to make sure that we follow all these marking criteria. And just to have another look at what we have right now here, um, let's move on to another video that I have it here. Let me just bring it to you. Okay, it's here. So let's see how we're gonna work with this. Let me just make it a little bigger for you guys to watch, and let's have a look at this one. Right now, you see here, we're gonna use the FPGA. You have the board and you have the oscilloscope in front of you. So here you can see pulses with a period of 500 milliseconds right here. See, and also you can see 200 milliseconds right here. So the larger one is 500 milliseconds. The smaller ones are 200 milliseconds. And over here, we can see a simple circuit that is here that we can use to visualize pulse with modulation. So this circuit consists of LED and 330 ohm resistor. Um, Now, there are only two wires coming out of the FPGA. Observe this P mod port. This back wire is the ground wire, and the blue wire is the signal wire. So we can have a look at this one, that how we're gonna do this. This is a lab experiment from a video. Let me just skip this and come back to this thing. Okay, so, and the blue wire is a signal wire, and the pulse with modulation signals are transmitted through this wire. So, you see this is the thing. So more detailed explanation of the basic circuit here. Let's have this and all the connections later on the video we will talk. So, these are simple approach to generate pulse with modulation. So you can always see all different kinds of boards as being shown here. So there might be other different forms. So the one you're using should be like this. So uh, let's see, have a look at very low code in all explanations to the link and the post. If you need, you can email me and I can send you more details. Um, so this thing, if you see the connections, this is how your board looks like, and then the way they are connected, and this is your board. So let's move on to the next segment. Um, so let's have a look. So other types of FPGA, the board is shown over here again. Um, the connections of the board with the external breadboard is shown over here. External breadboard is shown here. So let's explain this circuit now. If you look at this mod port over here, the yellow thing, I'm just showing it with the circle. It is used to interface the FPGA. So the ports of the pin mode are shown over here. The board over here is ground, and this is a signal. Basically, this is our signal, and this is ground. This wire over here will transmit full speed modulation signals that look like this. And if you see, what's one important thing is to keep in mind is the name of the pin is H4. This is very important for writing the constraint file, and we can explain this later on. Then to visualize pulse width modulation signals. So we created a small circuit over here. Basically, this circuit consists of 330 ohm resistor and LED. Basically, what happens over here? Uh, just I just stop it here, and you can see what we actually doing here. Um, that once mid-modulation signals are transmitted, and if this basically period is not very fast. When we say not very fast, we mean that this period is, for example, zero point 0.5 seconds. Uh, then the LED will blink. Basically, the LED will blink when we have high voltage, and it will stop blinking when we have low voltage. Consequently, we will have light, no light, light, no light, light, no light. So here we have a quick start. Let's start with coding notice over here. That's our um, uh, one of the Vivero software here. So let's create a project. This is an example. You can use other softwares as well. So here are some of the default settings. It's important to keep in mind that options and do not specify source at this time. Click on next. Let's find the boards. So you can click over here and you search for your board. So in our case, it's Nexus A7 as in the video, and here it is. We will check it. So now it's almost done. Okay, now we are ready to code. We need to create two files. The first file is our source file of the main file, and the second file is the constraint file. The source file will basically define the programming logic of our system, and the constraint file will be used to constrain the variables defined, or better to say declared in the source file, to the actual pins on our board. So let's create the source file. We will click on add sources, and over here we will select this option, add or create design source, and I click on next here. So I'll click on create file. I'll call my file, let's say main file. You can choose other name if you wish. I will click on finish, and I will click on OK, yes. And after some time, this window over here will update. We will click over here, and we will double click over here, and then this window will pop up, and here's our source file. So let's completely erase everything that is written over here. And in order to make this video as short as possible, I will basically copy and paste the code from the previous file we created. So here is my source file. So I'll copy and paste this file over here, and I will explain this file in details. This file is also given on the web page. If you go onto this video, so this is given over here. It's a source. This is a video from some of the links. So let's explain the source file here. We are using the time scale 1 nanoseconds with the precision 1 picoseconds. This is not important to understand for the time being. Then here I define my module. Here is the beginning of the module, and here is the end of the module. Um, the module has one input. The input is this variable CLK, which is shorthand for clock. So let's skip this thing and wait for the video to come, and then we'll continue from there. So if you see, this is a shorthand for clock, and the output is LED. Um, this module will accept clock, and it will produce signal LED. See, right here. Okay, so let us explain this module in more details. Let me draw this. Okay. Basically, our a module can be represented as a block. It accepts clock CLK, and it produces a signal LED. The clock variable for the clock input will be constrained to the system clock. So our current board has a clock of 100 megahertz. This means that the period of the clock is 10 nanoseconds. So let's visualize this graphically. Let this be a time axis t, and let this be a clock right here. So our clock looks like this. It is basically a very high frequency train of pulses. Where this period over here is 10 nanoseconds. Okay, and this clock is actually used as a reference to produce the pulse with modulation signals that this output LED is carrying, and the pull speed modulation signal will look like this. It will again be a train of pulses with this period denoted by T. And the pulse rate, let's say, denoted by T1 that are specified by the user, that is T1 and T, are specified by the user, and T1 and T are computed by using clock as the reference. So the clock is the smallest time unit that can be used to produce T1 and T. 1 over T is usually called a duty cycle. And let's say a duty cycle of 100% means that T1 is equal to T. That is, we have a constant DC signal. However, for example, T1 over T is 10. This means that this signal is 1, actually, the pulse with the is 1/10 of the period. That is um, our pulse with modulation signal looks like this. So this would be the situation. Uh, let's move on to the next segment. So you just try doing this, and then we will move on to the next.